Hello and welcome to TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name is Ethan, lead tutor for chemistry and biology, and in today's video we'll explore ideal gas laws. Let's get started. This is the second video in a series of two videos covering the ideal gas law. If you haven't seen the first video, I would recommend watching it before this one. A link for the first video is in the description below. In this second part, we'll learn the last two of the four individual gas laws, as well as a more complicated example where we'll solve for the density of a gas using the ideal gas law. Boyle's law is the first law we'll cover, and it involves pressure and volume. It states that pressure is inversely proportional to volume when the number of moles and temperature are kept constant. This means that if we take a container and squish it down its volume, the pressure must increase. This is like squeezing a balloon until it reaches a pressure that the material can't withstand and it pops. Our equation is P1V1 equals P2V2. Since N and T are constant, we just cover them up to derive our equation. Essentially, all we're left with is the numerator of our ideal gas law, so we get P1V1 equals P2V2. Here's a problem illustrating Boyle's law. We have 5 moles of argon gas maintained at 80 degrees Celsius. The pressure is 1.1 atm with a volume of 0.75 liters. If the balloon is squished down to 0.25 liters, what will be the new pressure? So here we don't need to consider the 5 moles. All that matters is the amount of gas doesn't change and the temperature doesn't change. We're given P1, which is 1.1 atm, V1 is 0.75 liters, and V2 is 0.25 liters, and we're looking for P2. We can set up our equation, solve for P2, and plug in our values. We end up getting a new pressure of 3.3 atm, and this makes sense. We decrease the volume of our balloon, which should result in an increase in pressure. Here we see the pressure change from 1.1 atm to 3.3 atm. The last of the individual gas laws is Avogadro's law. This law states that the number of moles is directly proportional to the volume whenever pressure and temperature are kept constant. So the more gas you add into a container, if you want to maintain constant pressure and temperature, you must increase the volume. The equation for this one we have is V1 over N1 equals V2 over N2, since we are keeping pressure and temperature constant. And here's our example problem. A container of 15 grams of oxygen with constant temperature has a volume of 2 liters. 12 grams of nitrogen are added in. What new volume is needed to keep the pressure constant? So the temperature and pressure are kept constant. We have the initial amount of gas, that is 15 grams of oxygen. We also have 12 grams of nitrogen gas that we're adding in, and we want to find out how the volume changes given an initial volume of 2 liters. First, let's convert our masses of gas to number of moles. For oxygen with a molar mass of 16 grams per mole, we get 0.93 moles. So our N1 is equal to 0.93. But our N2 is not equal to the number of moles of nitrogen. Our N2 is equal to our new total moles of gas, which is moles of oxygen plus moles of nitrogen that we add in. And therefore N2 is 1.79. Now we just plug in our values after solving for V2 and we get 3.8 liters. And now we want to check if this makes sense. We increase the amount of gas, so we should see an increase in volume, and we do. Here's some further application of the ideal gas law. Beyond predicting values of pressure or volume or temperature, we can actually use it to find the density of a specific gas at a given temperature and pressure. Here we have oxygen gas at 0.75 atm and 25 degrees Celsius. So our goal here is to find the density of oxygen gas at these conditions. Here we have two equations. We have the ideal gas law and the equation for density, which is just mass divided by volume. Let's try to solve for density in terms of just pressure and temperature. First, we can represent the mass as just the molar mass of our oxygen times the number of moles. Because molar mass has units of grams per mole, multiplying by moles gives us grams. So our mass, which is lowercase m, equals molar mass times N, where capital M is molar mass. Also, mass is equal to density times volume, found just by rearranging our equation for density. Now we have two values for mass that we can set equal to one another and solve for volume. Next, let's plug in our value for volume into our ideal gas law and simplify. We can cancel n on both sides and rearrange to set everything equal to density by multiplying density over to the right and dividing by RT. Now we have that density equals pressure times molar mass divided by the gas constant times temperature. Okay, so it looks like we have one equation and one variable, so we can solve. Let's plug in our values and make sure all of our units match. And for capital M, molar mass, we have to consider that the molecule we're dealing with is O2. So molar mass is 2 times the molar mass of one oxygen atom. Once we solve, we end up getting a density of 0.98, and our units are grams per liter, since everything else cancels out. Therefore, we can say that at room temperature, 25 degrees Celsius, and a pressure of 0.75 atm, oxygen gas will have a density of 0.98 grams per liter. Here are some good resources for all things related to the ideal gas law and the 4 individual gas laws. The link is provided in the description box below. It has various different units that you can use and values of the gas constant depending on what units you're given. Here's a picture of what is given in the link. You can see all the potential units for pressure and volume, as well as their conversions. Also on the top right are the values of the gas constant for various units. Here are the references for the images used in this video. Thanks for watching TutorTube. I hope you enjoyed this video. Please subscribe to our channel for more exciting videos. Check out the links in the description below for more information about the Learning Center, and follow us on social media. See you next time.